All right. Well, hopefully everybody had a good, restful weekend. Okay, here we are back in class again. So today we are going to cover, chapters 10 and 11. So we'll look at kind of a hodgepodge of topics. Glaciers, desert processes, wind processes, and geologic time. Let's see, process-wise, I think we'll talk about the midterm next class. Is there a question? Excuse me. Okay. Yeah, I think we'll talk about the midterm next Wednesday because really shouldn't be starting it until after we finish chapter 12 anyways. So we'll talk about that next Wednesday, so all that information is fresh in your minds. All right, anything else other than topics relating to the midterm that we need to discuss before we get going on the lecture today?
The midterm is March 28th, right?
So the midterm is due on the 22nd.
Okay.
Yeah. So we're going to finish chapter 12 next Wednesday, and that is the 15th. So you'll have at least 16, 17, 18, 19, 20, 21, 22. Yeah, a week. So you have a week to get it done. That's plenty. So let's hold off on that, and we'll talk about that next Wednesday during lecture. Okay. All right, just 1 minute. All right. All right, so let's go ahead and start with a look at glaciers. It's a very interesting subject, and hopefully, if you are interested, you'll be able to see one sometime in your lifetime. But you'll need to be quick about it because glaciers may not last the next 50 years. All right. Okay, so here we go. All right, so a glacier at a most basic level, okay, is just a big chunk of ice that sits on land, typically form in mountainous areas, though they can form over large land masses. I'll explain those here in literally just a minute. Basically, it's the process of adding snow from each year on top of the snow that was already added to the glacier the year before. Okay, every time you get another season's worth of snow added on the top, what happens is you basically start to pack the snow that's deeper down, pack it closer together, more tighter, kind of like a snowball. When you're packing it, really wet type snowball, you can get it really packed and pretty small sized compared to when you started out. Same concept. During the summer months, glaciers will, it's pretty common to melt back a little bit, okay? There's nothing unusual about that, but in order to be considered a glacier, all of the snow from that year cannot be melted, okay? So there has to be ice that survives year after year in order to be considered a glacier. Excuse me. All right, so there's two types of glaciers. There's valley, also known as alpine glaciers. Those are found in mountainous areas. And then there's ice sheets. These are large glaciers that tend to cover, when they are present, tend to cover large areas of continents. Okay. Another difference between the two is that valley glaciers aren't very thick. I mean, they can, they can be thick. What I would say, maybe like 300 feet thick, 500 at best, valley glaciers, but ice sheets can get to be upwards of a mile thick, so, over 5,000 feet thick. So it's a major difference there between the two, thickness-wise. All right, so all glaciers have one thing in common, and that is how they move, okay? So there's basically two zones within a glacier, and each of those two zones, the ice moves in different ways, okay? So there's plastic and brittle. Okay, plastic flow, which occurs in the majority of the glacier, and it occurs from the bottom up to somewhat close to the top. This is a zone where the ice is under pressure because there's a lot of weight above it, okay? All the ice on top and all the snow and debris adds pretty good amount of pressure because of the weight. And what happens is when things are pressurized, including rocks, we know that they can deform. Okay, they can deform plastically. Okay, in this instance, we're not adding heat. Okay, like often case occurs with rocks, but really, what causes the movement is the fact that the glacier, the ice within the glacier, is being pulled downward under the influence of gravity. Because remember, they're tend to be found higher up in the mountains, or in the case of the ice sheet, the middle of the ice sheet tends to be the thickest part. So it's still pulling in a downward fashion with gravity. Okay, so in the area of plastic flow, okay, the ice moves by deforming essentially. So it deforms, it moves plastically, essentially atom by atom, okay? Now, let's see. A brittle flow, which occurs at the very top of the glacier up here, okay? This zone of the glacier, when it moves, it will often fracture, and that's because of that lack of pressure, okay? So anytime pressure is put on it, yeah, a crack is going to form, okay, and it'll just crack. It can also move along with the plastic zone below it as well. Okay. Now, the brittle zone also includes those cracks that we know to be called crevasses. Okay, so crevasses are surprisingly, they can be surprisingly deep, but typically they're not going to go below about 50 meters deep, and that's about 150 feet. And that's because that's the point at which the brittle zone ends and the plastic zone begins. Okay, so crevasses don't form in the plastic zone because it's not brittle. Okay, see a couple other things about this picture before we move on as it relates to movement. So I want you to look at these red dots. Okay, the red dots represent the tops of pipes that have been drilled down through the glacier into the bedrock directly beneath it. Okay, over time, what happens is, well, you start out here. Okay, so you get some glaciologists, they drill a handful of pipes straight across the glacier. Okay, they come back a year later, let's say, and they notice that the pipes have now moved down slope, and they have this kind of trough type appearance, like a U appearance. Okay, now what's happening there is actually not that awful difficult to understand. because we looked at this concept when we talked about streams, where the outside edges, so in the case of the stream, the banks of the stream and the bottom, though they provide friction, okay, and friction slows down the adjacent water next to it. Same concept here, where we have the rock walls of the valley, and the outside and the bottom of the glacier are in direct contact with those rock walls. So there's a substantial amount of friction, okay, and that's holding back the edges and the bottom, okay? So notice that the sides and the bottom don't really move that awful fast, at least in relation to this stuff in the middle, okay? In the middle, where there's a lack of friction, okay, you'll notice that the ice actually flows downhill faster, okay? So that's kind of how that works. Another look at it is from a side view. Whereas if they drilled a straight pipe, it came back a year later, what they would have noticed was the pipe has moved down valley a little bit, and that's to be expected. But in addition to that, the pipe is being deformed because it's essentially because it's moving down in a downslope fashion. Okay, same concept with the friction. Here we have more friction at the bottom, less friction up here towards the top. Hence, the top of the pipe is moving faster down in a downhill way than the bottom of the pipe. Okay, so a very dynamic process there associated with glacial movement. Now, glaciers can erode by a couple different ways. First way is through plucking. Okay, plucking is loosening and lifting solid rock that has typically this solid rock has been jointed, so cracks have formed within the solid rock. Okay, and that's normal. It's a normal process. Then through the freeze-thaw cycle that we looked at last week, I believe it was, we know that during the daytime, if temperatures get above freezing, ice can melt, the water can get down in those cracks, refreeze that night, and pry apart those rocks. Okay, so the freeze-thaw cycle that's associated with mechanical weathering is a very important way that allows plucking to happen. Okay, so the loosening and lifting. As the glacier is moving in the downhill direction, which is from right to left in this case, it's literally the ice being in contact with the bedrock. It actually will freeze to the bedrock, and that will also help facilitate plucking. So basically, we'll freeze onto pieces of bedrock, and if the glacier moves, it'll just pull it right out, so it'll pluck it. Okay, so it plucks, and then typically just carries that material along with the glacier. Okay, so there's always going to be a substantial amount of rock material, you name it, all sorts of stuff, ranging in size from clay and silt sized all the way up to huge boulders that are going to be plucked from bedrock and then carried by the glacier. Okay, another way is through abrasion. Okay, that's just simple scraping. Okay, so we know that ice is pretty hard. Ice generally, it won't scratch rock, but what ice can do is ice can freeze to rock pieces, and it can pull those pieces along, and those rock pieces can scratch and abrade at other pieces of bedrock. Okay? That's kind of how abrasion works. I mentioned what I just mentioned kind of was the concept of striations. Those are straight kind of grooved appearances cut into solid rock. Okay, that's when the glacier picks up rocks that have already been plucked and basically carries them along, and as it moves downhill, that rock literally just scratches a straight line downhill in that solid bedrock. Okay. And this whole process in general, as you can imagine, is kind of like sandpaper. They create all this grinding that's associated with abrasion, creates a significant amount of debris, very fine material stuff like silt and clay size. And so a good amount of that stuff will end up being discharged from the glacier through subglacier streams. So streams that typically flow at the bases of glaciers. It'll carry that material out through the end of the glacier, the terminus, and down to local waterways and lakes. So if you ever go to the mountains and you see a really neat turquoise colored lake, that is actually what's called rock flour. That's so silt-sized or very finely pulverized rock material that's been abraded from bedrock by a glacier. Okay, that turquoise color is the result of sunlight reflecting off the silt. Okay, so really, really neat. If you ever get the opportunity to see it, that is just such a great picture. Okay, before we move on, are there any questions on the erosion or the movement of glaciers? Okay, all right, well, let's go ahead and talk about some glacial landforms then, that are erosion landforms, rather. So the first is the main trough. It's called the glacial trough. It's basically the main valley in which the main glacier resides. Okay, so in this instance, what you're seeing is this glacier is found within the main trough. Okay, and then often what happens is kind of like with streams, you have tributaries. Okay, there's kind of like little side mini glaciers that come off from the main glacier. Okay, those form in what's called a hanging valley. Excuse me. They will erode their little valley, individual valleys, the same exact way that the main glacier will. And notice that it's a very characteristic U-shaped erosion pattern, and it looks almost like somebody's taken sandpaper and just made a very nice, smooth, sandpapery U. Okay, that is the abrasion. Okay, abrasion via very fine sized material like silts and sands mainly. So very fine material stuff that really makes it look smooth when it's been abraded a lot. Okay, some other features, and keep in mind this is for alpine glaciers here. Okay, so glaciers you find in the mountains. Up at the very top of these basins, where the top of the glacier is it called a cirque? A cirque is kind of a bowl-shaped depression where, again, where the top of the glacier resides. It's bowl-shaped because of the very unique way that the top of the glacier starts to erode. Okay, but yeah, it takes on that very unique bowl-shaped appearance. Typically has a lake in it. Then there are arêtes. Arêtes are basically mountain ridges that separate different valleys with different glacial arms coming off. They're glaciated as well. Arêtes tend to look very spiky, and again, that's because of the abrasion, so it looks very well sandpapered. Horns tend to look like pyramids. Those are mountain peaks that are glaciated. Okay, so they're well shaped as well. And then you can see some other minor features like tarns and paternoster lakes. Those are just different types of lakes that are found within these valleys. Yeah. And the last thing is a fjord, which isn't shown, but a fjord is a glacier that terminates at the ocean or just some large body of water. So most of the glacier is on land, but the very end of it at the bottom, the terminus, actually floats on the water like an ice cube. Okay, so that's erosion processes. Now let's switch gears here, take a look at depositional processes. So all material that has a glacial origin is just generally referred to as glacial drift. Okay? Now, glacial drift gets broken down into two different types of material. Okay? The first is called till, or glacial till. Okay, that's this picture over here on the right side. That's just basically a unsorted, jumbled mess of earth materials of all size. Okay, that's typically how you find it in a glacier. Okay, once the material's been plucked and abraded, it all tends to kind of just mix together into a big jumbled mess. Okay, then there's stratified drift. The difference with stratified drift is that this stuff is well sorted and it's layered. So we know that stratified drift is sediments that are glacially derived that are sorted by those water from those subglacial streams. So you get those streams coming out at the bed, with the glacier, and the waters are very sediment rich. Okay, bringing a lot of sediments out. And typically, they'll get deposited in flatter areas in front of the glaciers, and then they'll be just deposited in these flat sheet-like appearances. Okay, so that's stratified drift. And erratic isn't a type of glacial drift. It's kind of a category of its own, I guess. Simply put, an erratic is just a huge boulder that was being carried along by a glacier, and it was either dumped over at the end of the glacier, at the terminus, or it was dropped wherever it happened to be when the glacier melted back. Okay, it could happen either way. Oh, so a lot of times you'll actually see erratics in farm fields in the Midwest, because these are often associated with ice sheets. And so if you're driving along and you see a big boulder in the middle of a farm field, you'll know that is an erratic. That certainly doesn't belong there, and that's because the glacier left it there. All right, another depositional feature of glaciers are moraines. Okay, there's I believe four or five different types, classifications of moraines. The two main ones are lateral and medial. So a lateral moraine is merely just the sediment that builds up on the edges of the glacier on both sides. Okay, so as you get plucking and abrasion, all that sediment a lot of it will build up on the sides. Some of it will end up on top as well. Then there's medial moraines, are basically when, because all these individual little subglaciers are flowing downhill, they'll eventually coalesce with the main glacier in the main valley. Okay, and then what's going to happen is going to get a striped appearance. Okay, that striped appearance is individual glaciers that coalesced, and in between them are the lateral moraines. So here we have lateral moraine that was squeezed in between these two glaciers when the two coalesced. You're seeing the formation of a medial moraine right here. Okay, there's one right here. Okay, and then two other more common types of moraine. The end moraine, also known as the terminal moraine, is just simply the furthest advance that the glacier has ever made in downhill. Okay, so this typically represents the extent when the glacier was at its largest. At its largest. Okay, so typically glaciers, they're kind of like conveyor belts, and what happens is all the sediments and materials that are moving along with the glacier, eventually that material will make it down to the terminus of the glacier, and then it'll be dumped off the edge. Okay, and again, in the instance where it's the furthest advanced downhill, that's the terminal moraine. But oftentimes, what will happen is a glacier will retreat back uphill in warmer years, and then it'll advance back downhill on colder years. So you have this kind of seesaw action year by year, and as a result, what will happen is ground moraines will form. Those are just simply moraines in general that form as a result of the seesaw action. Okay, so let's say the glacier starts melting back for a couple of years. It'll actually still form moraines as it's moving, as it's retreating back uphill. Okay. One thing I want you to understand about glaciers is that when snow, let's say snow falls up at the top of the glacier, and that snow gets turned into ice, that piece of ice does not just sit up there in that same spot for the rest of its life. Okay, ice within the glacier is always moving downhill under the influence of gravity. So that means that that piece of ice that initially forms way up toward the beginning of the glacier, high up, over the years is slowly moving downhill, or down through it's being transported downhill, kind of like a conveyor belt. And then eventually it will find itself at the terminus of the glacier, and it will likely be melted off at some point during the summer months. Okay, so you see that glaciers are a very dynamic process. There's a lot going on with these things. Okay, here's some other depositional features that are associated with ice sheets. Okay, ice sheets, remember, are the huge ones that cover large continental areas. And our last ice age here, which was the Pleistocene, which ended about, it depends where you're at, 10, 13,000 years ago. Before then, there was actually a huge ice sheet covering all the Midwest. And it's slowly retreated northward as climate has warmed. But anyways, what we see today are depositional features associated with that ice sheet. Okay, so I know you guys have seen these kettle lakes. A lot of people go up to Wisconsin, southern Wisconsin, to go boating and whatnot, go fishing, whatever your cup of tea is. Those are kettle lakes. They're little dinky lakes that often aren't interconnected with like water, with streams. They just appear to be solitary lakes. Okay, kettles are formed in a unique way. Okay? We know that ice sheets and glaciers, but ice sheets more specifically, ice sheets are huge and thick, so they weigh a lot. So we know that ice sheets depress the crust, Earth's crust, okay? Basically smashes it down and compresses it. And what happens is when ice sheets retreat, the ground surface begins to slowly rebound upward. Oftentimes what will happen with kettles is that large chunks of the ice sheet on the edge will cleave off. They'll basically crack off, and they'll just kind of fall to the ground. But they're heavy enough where they still depress the ground materials, the sediments. So they create a depression. Then when that chunk finally melts, the water just typically is retained in that depression. And so initially the water from the kettles is from the little chunks of the glacier that fell off, but of course they're recharged nowadays by precipitation and groundwater. Let's see here. Drumlins, that's these guys up here. Okay, these are teardrop-shaped hills that are tapered from the head here down to the tail. And we know that the direction of ice movement is from the head to the tail. So in this case, from left to right, because we know that the steep head part, there's always an obstruction that creates that. Okay. Typically, there's also a void, like a cavity within the glacier that's empty, and what will happen is material will, so like sediments, will move around this obstruction, and then they'll fill in behind the obstruction, resulting in the formation of the drumlin, and then it gets tapered off as the glacier continues to move in that direction. Okay, eskers. So eskers are basically former subglacial streams. Okay, those streams that I was mentioning that often carry a significant amount of sediments out of the glacier at its base. So yeah, basically what you're seeing is just what you would find at any stream channel. Okay, sediments on the bed. It's just that the eskers form as kind of a sinuous ridge, or kind of like a snake-like hill type appearance, because the subglacial streams are basically kind of like flowing through a cave. Okay, so the stream is just merely flowing through empty voids at the bottom of the glacier, and so as it's carrying sediments along with it, it also deposits a fair amount of sediments as well. Okay, so these eskers, they can be pretty large in size because there's just a lot of sediment that's provided. Let's see. And then lastly, kames. So kames are just big mounds of stratified drift. Okay, so sorted and layered material. These tend to form in just voids that form within a glacier as well. Okay, so sediments just find their way to the voids by water. Okay, so they're associated with eskers, and basically the stream just dumps sediments into a big hill. That's about as simple as it gets. Okay, so yeah, you can see these features in our area. If you go out by Waubonsie, the community college, hold on just a minute. You can see a lot of these features out in that neck of the woods. It's called Bliss Woods Forest Preserve. You can see an esker there. There's a kame not too far away. The other drumlins and drumlins and the lakes, I don't think are over there, but you can find those in other places. Also, Johnson's Mound out in Kane County, that's a forest preserve. That is a huge kame. So definitely worth checking out because it's right in your backyard. Okay, so are there any questions about the nuts and bolts of glaciers before we kind of move off that topic? Okay. All right, so as promised, here's a look at the last ice age. Okay, this occurred during the Pleistocene. So as you can see, this big ice sheet was called the Laurentide Ice Sheet. Okay, it basically retreated northward, so now it only resides in Greenland here. Okay, but as you can see, it came down into the southern states, so it came quite a way down. So the ice age itself actually consisted of multiple surges of the ice sheet. So it would, you know, there would be minor variations in climate. So it might surge southward on especially cold years, and then might start to melt back and retreat during warmer years. Okay, but there were certain periods where um, there would be either surges or retreats for pretty long periods of time. So the last surge that happened before this ice sheet fully retreated north actually only came down to our area before it moved before it started to recede back up north as climate began to warm up around 15,000 years ago, depending on where you're at. So you can see that this ice sheet at its maximum extent covered about 30% of Earth's landmass. Okay, so very large in extent. Also included most of Europe and a good chunk of Asia as well. Okay, so what were some of the effects of this glaciation? Okay, one is we know that stream channels were changed. Their routes were, for instance, like the Mississippi. Actually, if you look at the bedrock map of the U.S., you'll see that Mississippi had once carved in bedrock its channel, but once the ice age occurred, its channel was shifted into a different course. Okay, so that was pretty common. Crustal subsidence, as I mentioned, because these ice sheets are can be a mile thick, over 5,000 feet thick, they are very heavy and they will smash down the Earth's crust. Okay. Then you also have migration of animals and plants toward the equator. So basically migrating south toward warmer climates rather. And then, of course, worldwide drop in sea level as a whole bunch of ice becomes entrained into this huge ice sheet. Okay, so what are the causes of glaciation? Okay, it's thought that perhaps the supercontinent cycle that's associated with Earth's plates coming together into a large continent. It's thought that maybe that plays a role because we know that one large landmass actually wreaks pretty good havoc on climate. Okay, but that's not thought to necessarily be the main driving process. What's thought to be the main process is called the Milankovitch hypothesis. Okay, this is really more of a theory at this point because it's been well tested and it has not been debunked as of yet. And I don't anticipate it will be, but who knows? You never know. But this, I think it provides a good explanation of why glaciations occur. So basically, you've got three different astronomical variations that occur. So how Earth is in position in relation to the sun. Okay, that's critically important. So first, we have what's called eccentricity. As Earth is revolving around the sun, its revolution, its shape rather, can be anywhere from a circle to more elliptical or egg-shaped. Okay, and I don't have the time frames listed, but just know that these three individual astronomical variables, they occur on during set variables, and there are only certain times in Earth's history when the three have matched up. And those are the times when massive glaciation has occurred on Earth, okay, because it's happened a couple times. Okay, so we have the eccentricity, that's the shape, the orbit shape. The tilt of Earth's north-south axis, that's called obliquity. Okay. We know that the obliquity can range between 22 and 24.5 degrees tilt. Okay, so basically, what is that doing when it's tilting back and forth? Well, it's basically changing where sunlight's being received, okay, and how much sunlight is being received. Because remember, Earth is round, okay. So when you change the tilt, you can cause substantial changes in the amount of sunlight that's being received at a given location. Then the last process is called precession, okay? So also referred to as wobble, okay? Because that's kind of what you're seeing here. So wobble really takes into, or the precession takes into effect both obliquity and eccentricity. So basically, you have the Earth rotating around the sun, okay, once every 365 days. And in addition to that, you have the Earth rotating once every 24 hours, okay? And so those two movements combined, along with any change in the tilt, if that does happen, creates this kind of wobble-like appearance, okay? And that wobble is referred to as precession. Okay, so actually that's it for the glacier portion of the presentation. Are there any questions relating to glaciers before we move on to deserts? Okay, all right. So what I call deserts, that's really a misnomer. Okay, any area, any land area where a water deficit exceeds water received. Actually, hold on, let me reword that. Make it more simple. So anywhere where evaporation exceeds precipitation, there we go, is called a dry climate, okay? Now, dry climate's really broken down into two categories. So desert and steppe, okay? A lot of us, myself included, I tend to just say desert for anything that's dry, but technically steppe is a less dry area, so a more moist area that's still dry, but it's an area that surrounds the fringes of the desert areas. So you see the bona fide driest areas in yellow. Then the areas that fringe the outsides are these tan-colored steppes, okay? So notice in the western U.S., most of the western U.S. is actually steppe or desert, mostly steppe though. And that's pretty evident when you go out there. Anywhere out west, with the exception of the West Coast itself, you'll see pretty sparse, meager vegetation out there, and that's pretty typical of steppe environments. So in these dry climates, weathering tends to occur less due to the lack of water, okay? So that's kind of a look back at what we discussed when we talked about surface processes. We noticed that weathering is most efficient in warm, very moist environments. Deserts are the exact opposite of that. So weathering doesn't occur nearly as much. So believe it or not, rain or precipitation in general is actually, well, let's leave it at rain. Rain is the predominant driver of weathering when it does occur, okay? And that's because flash floods tend to occur in the desert. Okay, a lot of times in the afternoon hours, especially during the summer, just because of the way heat rises, okay, thunderstorms will often develop early afternoon in the dry areas. Okay, see, a lot of times you might get a quick shower, but I can attest many times that I've seen bona fide thunderstorms with heavy precipitation in super dry areas. And what happens is, because those areas, the soil is just consistently baked by the sun, right? It's just dried up completely. Soil, when it gets baked like that, baked by the sun for long periods of time, it becomes hydrophobic, and that basically means that the soil develops properties where water has difficulty infiltrating through it. So that means that when flash floods occur as a result of these thunderstorms, a lot of times the water, not much of it will infiltrate in through the soil because of that hydrophobic nature. A lot of it will run off right on the land surface and then run down to the low-lying areas, which are these things. They're called washes. Basically, they're intermittent streams, also known as ephemeral. So there's only water in these streams when there's storms and whatnot. Otherwise, they're dry. Okay, so flash floods actually cause pretty dramatic erosional changes, even just with one thunderstorm event. Okay, if you get enough water, that water has a lot of power. So having said that, water is the predominant vehicle for erosion in dry climates. Some features that are associated with dry climate areas. These are typically associated with the Basin and Range Province, which is that area which encompasses mostly Nevada, Eastern California, and kind of Western and Southern Arizona. It's an area where the crust of the North American plate is thinning, because remember, it's the North American plate has heavy Rockies on one side, or the heavy Rockies and the heavy Appalachians, and then you have the heavy Sierra Nevada and California over on the western side, and those are causing kind of an arching appearance to occur on the North American plate. Okay, so that arching appearance is causing cracks to form in the crust. So that's what we call crustal thinning. So the Basin and Range is that area where a lot of crustal thinning is occurring, and that tends to emanate as horsts and grabens. Okay, we looked at those last week. Horsts are the higher mountainous looking areas, and the grabens are the downdropped fault areas that look like valleys. Okay, so if you ever drive through Nevada, Highway 6 or Highway 50, it's not as boring as you think. It's actually quite interesting, but you will literally drive across probably a series of 15 of these horsts and grabens as you go west to east or opposite. Okay, basically, you're always driving up or down in that state if you're going east-west, but it's just series after series of horsts and grabens. So, so some of these features associated with that environment, alluvial fans, okay, those are really unique. They're interesting to see. They're basically just areas where sediments coming down from the higher mountainous areas, the horsts, the streams are bringing those sediments from the mountain areas down into the valleys, the grabens. And once they reach the valley, the water slows down and deposits all that sediment that it's carrying. It just naturally has a tendency to deposit in that kind of fan shape that you're seeing here. Okay, a lot of times you can be driving across these things out in the boondocks, and you won't even notice you're driving across one until you really take a close look. They're really, they're huge in scale typically. Then we have the Hada. That's just when two or more alluvial fans coalesce to become one. So you can see right here, that's kind of beginning to start. Playa lakes are basically the lowest areas in these valleys in between the mountains, where when there are thunderstorms and whatnot, water from the whole watershed will drain down into these valleys and create these temporary lakes called playa lakes. Okay, it's important to understand that in a lot of dry climate areas like the Great Basin, for instance, drainage patterns are often called internal. That means that there is no drainage pattern. Streams actually they just run to valleys in between the mountains, but then they end. The water doesn't actually discharge anywhere. The water will collect in the valleys, and then over the next week or whatever, because of the heat and the dry environment, all that water will just become evaporated within a week or two. Okay. Lastly, mountaintops in these areas are called Inselbergs. All right. So I guess that's it for the desert book. Any questions on the deserts or dry climates? Okay. Let me just check here. Come on. Where? Okay. Just checking to see if there's anything in the chat, and there is not. All right, so let's go ahead and move on to chapter 11, geologic time. So first, you need to understand that what we know about Earth history is predominantly from looking at sedimentary rocks and their structures, as well as the fossils that are encased in those sedimentary rocks. Okay, so sedimentary rocks are just hugely important when it comes to decrypting Earth's history. So in order to do that decryption, we need to understand how sedimentary features form, okay? So first we're going to talk about unconformities. Okay, so unconformities are just simply an erosional surface. Anywhere where you had existing sedimentary strata or existing sedimentary rock beds deposited already, any instance where erosion starts to happen to those beds, that's referred to as an unconformity. Okay, so there's three different types of unconformities. First is a nonconformity. That's where you have the existing rock at the bottom is either igneous or metamorphic. Then you get an erosional event. Okay, then after the erosional event, for whatever reason, and there's always a different reason for every place you look at, but for some reason, and climate usually plays an important role, deposition of sedimentary rocks begins on top of that erosional surface. So you can see sedimentary beds are laid down, okay? They're laid down flat or horizontally because of gravity, and they just cover up the erosional surface, okay? So pretty cut and dry. A disconformity is pretty much the same exact scenario, except the rock on the bottom in which the erosional surface. So the rock below the unconformity is sedimentary, and the rock above the unconformity is sedimentary, okay? In that case, it's referred to as a disconformity. Okay, the third type is called an angular unconformity. Okay, this is where you have older sedimentary, well, it can really be any rocks, quite frankly, but typically it's older sedimentary rocks that are deposited flat on the bottom, okay? Then what happens is those beds become deformed, okay? So So those beds are essentially tilted from a flat lying appearance up to, in this case, they're about 45 degrees tilted. So they look like they're kind of slightly tilted to the side. Okay. It's important to understand that those tilted beds initially formed as flat. Okay. They did not form tilted. Okay. Now, what's also critically important here is to understand that this erosional surface, which is in this case is called the angular nonconformity, it's called that because it's an erosional surface that separates angular, essentially angular or not flat, basically tilted. It separates tilted layers from a flat lying layer above. Okay, so you get the deformation of the bottom rocks, then you get the erosional surface after the deformation occurs. Okay, then after that erosion occurs, then you get new sedimentary beds that come in and deposit. Okay, so that's the more complex of the three, but it's really not that awful complex, quite frankly. So here we're looking at the what's called the stratigraphy, basically the sedimentary rock makeup of the Grand Canyon. Okay, and what you can see is there's a whole lot of stuff. Okay, but of all this information, what's interesting is to point out some of the unconformities. Okay, so down here we have a nonconformity. That's an erosional surface between the oldest foundation rocks, aka the basement rocks, which are metamorphic, and a younger sedimentary, younger sequences of sedimentary rocks above that nonconformity. Okay. Okay. Then right here we can see there's an angular unconformity. So that just means that before this erosional surface occurred, this Unkar group was tilted. Okay. And in this case, it was tilted, whatever, 40 degrees or something from left to right. It's kind of tilted up in that direction. But anyways, so you get the tilting, the erosion, then you get the deposition of these new sedimentary strata on top. Okay. Then you got a disconformity up here. That's just an erosional surface between the two different sedimentary beds. Okay, so just an interesting way to classify erosional surfaces in terms of sedimentary rocks. Okay. All right, so now we're going to move on and take a look at something a little more complex called the principle of cross-cutting relationships. So, this probably looks, pretty busy, complex. In all reality, it's not that awful difficult. What you have to do here is, this is basically, in order to decrypt what's happened here at this unique site, we need to understand a few basic concepts of how sedimentary rocks form. Okay, so first, actually, I think I'm missing part of the thing, but anyways, no worries. So first we have to understand that if one type of rock cuts through another type, that means that the rock that's doing the cutting is newer than the other one that it's cutting through, because the rock unit has to be there already in order for something to cut through it. Okay, so we know that this greenish bottom layer here was already there before dike A formed. Okay, same thing with faults. We know that the sedimentary strata that are affected by a fault, they all had to already be there before the fault formed. Okay. And so, you just take it step one step at a time when you're trying to figure these out. So there's some clues, to help you kind of figure these out. Like for instance, fault B here gets cut through by dike B. So that means that dike B formed after fault B formed because dike B cuts through the fault. Okay, so just small nuances like that are what helps you decrypt some of these really oddball situations. I don't think any of you will ever have to be in the situation to do this, but if you ever go to the Grand Canyon or something and you're looking out there at all these different layers, using this information, you can say, okay, yeah, I think I have a decent idea of kind of how that formed. So it's, in a way, it is kind of useful. So I'm not going to go through here and, this is a step-by-step look at how this specific setting formed, okay? But I do encourage you to come back and look at it after class, before the midterm, because there probably will be a question that's something related to this. But on top of that, what you're seeing here is also critically important, when we talk about the structure of sedimentary rocks. Okay? It tells the story of how this place formed, essentially. Okay. All right. Before I go on to talk about fossils, are there any questions about the unconformities? Okay. All right. So fossils, okay, are the remains or traces of remains of prehistoric life that are trapped within the sedimentary rock record. Okay. Fossils only form in sedimentary rocks because igneous rocks will get too hot. They would melt, or not melt, I guess, but they would destroy any sediment, any fossils. Metamorphic rocks also get too hot as well. They would destroy any fossils. Keep in mind that most fossils of living things, well, all living things are made of carbon material, including people, people, trees, plants, whatever. We have our bodies are made of carbon, okay, and carbon. Let's see here. Actually, I'm going to hold off on that because we'll get to it later in the presentation. All right. So then let's go ahead and take a look at some individual types of fossils here. Okay. So first, we're going to look at petrified wood. Okay. Petrified wood is something that you'll definitely almost likely come across at some point in your life if you ever go to any national park or something. Okay. So let's talk about what is it. Okay. Petrified wood forms as a result of permineralization. Okay, so this can occur for anything that has carbon material. So, like I said, anything that was once living. In this case, petrified wood is typically made from old trees. Okay, so here's what happens: you get old trees, they die, they fall over, and they become called rapidly buried. Okay, and this is typical for all fossils. Okay, oftentimes fossils are only preserved because they become very quickly buried by sediments or whatnot. Okay, and why rapid burials is important is because rapid burial, when you pretty quickly cover up something that died with sediments or whatnot, what you're doing is you are trapping out oxygen. Okay, and oxygen is a critical component of the decomposition process. Okay, so with any fossils, when you rapidly bury them, the oxygen gets trapped out and decomposition either stops or slows very, very slowly. In the case of petrified wood, here's what happens. The tree falls down, becomes rapidly buried in some way. Over time, we know that both surface water and groundwater contain dissolved mineral material, right? Like calcite, for instance. We know that there's a substantial amount of dissolved calcite, aka calcium, dissolved in our water. We just can't see it. So it's there. And what happens is these dissolved minerals, they will actually take the place of the organic material itself. Okay, so the structure of the organic material is left, but the precipitated mineral matter will come in and it will fill in those structures so that they retain their original looking structure. Okay? So when you look at a petrified log, you're not actually looking at a tree per se. It has no carbon-based material in it anymore. It's typically they're filled with silica, okay, dissolved silica that's precipitated. And like I said, the silica just comes in and literally just takes the place of the organic material. Molds and casts, okay, these are, one goes with the other. So a mold is basically the shape of some sort of critter, some sort of fossil, okay? Just like what we saw with the petrified wood, what we're looking at with this sample of a trilobite is not actually organic material. It is, again, precipitated mineral material that has taken on the structures of the organism, while the what is left of the organic material, the carbon, has decomposed over time. Okay, so very same process. A cast is just simply the outside impression of the top of the mold. Okay, so you can see the shell. This is an impression of the shell. Okay. Carbonization isn't as common, but this is the one example where organic material does actually remain. So what happens here during carbonization is that you get something carbon-based that dies, like a bee. It gets quickly encased in very fine sediments, okay? Another key thing about carbonization is that typically you see this occur in swamp environments which are already oxygen deficient, okay? So that's a plus. So in these swamp environments, then you see the rapid burial. So, trees, ferns, all that stuff dies, falls down. It adds additional weight on top of the material, squeezes on the material, compacts it. And what you end up with, carbonization, is essentially just a film, a very thin, flat film of carbon residue, but it still retains oftentimes a flat version of a 3D look at the object. Like in this case, the bee looks like a bee, but it's just a flat look at a bee. Then impressions are a lot like the petrified wood again, where you have something that dies. The carbon material decomposes and then gets filled in with some sort of mineral matter, and it retains the shape. Okay, bones typically retain their original carbon material. So when you're looking at like a dinosaur bone, that's most likely an actual bone, actual carbon material, but they can undergo that process where the carbon material has been decomposed away and filled with mineral material as well. I've seen both instances. Okay. Some other categories here. So preservation in amber. Amber is just simply tree sap. Okay, it's a very good preserving agent. And then there's some kind of oddballs like coprolite that is fossilized dung, okay? But I do want to stress that it's not actual dung anymore. The dung component, the feces, is carbon material, but just like what happens with most fossils, that carbon material decomposes and gets replaced immediately with some sort of mineralized material. Okay, so coprolites are just they just look like dung, but they're no longer dung. So you can touch them, smell them, whatever you want to do. Another thing is called a gastrolith. These are stomach stones that were used by ancient, now extinct type of reptiles that are kind of bird-like to grind food in their stomachs. In a lot of ways, present-day birds have a kind of a similar process where you'll see them occasionally eat, like chickens will peck at very fine gravel. They're actually using that gravel in their stomachs to kind of grind up the other food that they're eating. Okay, that's why they do that. Okay, then I think the last topic here, let me just double check. Yeah, last topic is radioactive decay. So with radioactive decay, basically when something dies, it starts out with 100% of its what's called parent material or parent isotope. Okay, after a set number of years, half of that radioactive material has decayed, okay, and that's called a half-life. Okay, so for carbon, for instance, carbon has a half-life of just over 5,700 years. So that means that when a tree dies, it contains 100% of its parent material. After 5,700 years, you dig up that tree, and it would only contain about 50% of its original parent materials. At that point, one half-life has gone by. Okay, give it another 5,700 years, two half-lives will have gone by, and half of the 50% will have radioactively decayed. Okay, so that's what this curve means here. Okay, hopefully this helps. This description here, I pretty much just described it, but radioactivity is one of those things where it's hard to kind of not understand exactly how it works because it's kind of confusing, but hopefully that does help. So I did use the example of carbon-14 for dating. Okay, carbon is what's found in all living material. So all living material will take up carbon-12, 13, and 14 isotopes. Carbon-12 is the most prominent. 13 and 14 are the two that are radioactive. Okay, so this is an age dating method that's used predominantly for relatively recent events. So mainly archaeologists and paleontologists use carbon-14 dating pretty extensively to figure out ages of things like charcoal, found in fire pits from ancient dwellings, tree rings, things like that. Okay. Okay, so that's it for geologic time, and we are right at the end of our class, but I will entertain any questions that anybody has about anything that we looked at today, if anybody has any questions. Okay, not hearing anything. We'll go ahead and conclude for the day, for the week rather. And next Wednesday, we will cover the last chapter, chapter 12. So last chapter that's included in the midterm, and then we'll talk about the midterm. Okay, so make sure to show up to class next Wednesday, and we will talk about all that stuff. So you guys have a good weekend, and I'll see you next Wednesday.